We're going to look at parabolas and think about any shape that is like this or like this. We'll have a place where it reaches a maximum value and turns around, or a minimum value and turns around. And from a like an engineering, physics, economics point of view, this is usually where the interesting stuff happens. So if, for example, this was a projectile or you were launching something, a maximum height is something you'd need to know, especially if there is a ceiling that you have to stay under. Minimum values, if you're trying to set a ball rolling on something and you want to see where an object will get trapped, I mean, that is what you'd be hunting for there. If this was a finance question, right, and the value of your stock profile is doing this, you would want to know when that happened, because you should be buying stocks then and you should be selling them there. So there are lots of applications for finding max and min values, and there's a whole branch of mathematics called calculus that helps you do this for any function. But we're not quite ready for that, so we're just going to start talking about parabolas. So first off, if I look at the lead term here, it's positive. That means it's an upward oriented parabola. So the vertex, which happens to be the max min of a parabola, will be down here. So for this particular one, I'm going to be finding the minimum value because of its upward orientation. Well, if I look at this particular information, I don't have the vertex. This is not in vertex form. So I'm going to have to find that. Now, there are a couple techniques you could use. You could use completing the square to try and turn this into vertex form. Or you could try factoring it to try and get the x-intercepts. Or if all else fails, you could go with a quadratic formula to find the x-intercepts and then go from there. Now I'm going to choose that third option because it's going to prove a point for us later. So I'm going to start with x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. That's your quadratic formula. So my a value is whatever's in the lead here. So I'm going to have an a value of 1. My b value is whatever's attached to the x. So it'll be negative 12. Oh, a little invisible spider friend here. Be gone, arachnid. And my c value will be 27. So I'm going to put 1, negative 12, and 27 into my quadratic formula. Negative 12 plus or minus negative 12 squared minus 4 times 1 times 27 all over 2 times 1. Okay, I'm going to try and not get this on my face. Negative 12 would be 12 plus or minus 12 squared is 144. 4 times 27 is 80, 90, it's 108. Two times 1 is 2. All right, 12 plus or minus 144 minus 108 is 36. That's a handy number to have in a square root. Square root of 36 is 6. So I have two cases. X is 12 plus 6 over 2. Would be 18 divided by 2, which is 9, or I have 12 subtract 6 over 2. 12 minus 6 is 6, divided by 2 gives me 3. So I'm going to put a grid up here. I'm going to plot those 2 points. Myself an axis. That's going to be too low. All right. So I have an x-intercept at 3. 1, 2, 3. And I have an x-intercept at 9. 4, 5, 6, 7, 8, 9. And after that, I still don't have the vertex, but I can see where it crosses the x-axis. And I know that these things are perfectly symmetrical. So there's an axis of symmetry here, dead center between those 2 roots. So I'm going to find it. They are 1, 2, 3, 4, 5, 6 squares apart. So 3 squares in from this one and 3 squares in from that one. I'm going to end up with this axis of symmetry. And that's happening when x is 6. Okay. Now I don't know where the vertex is vertically, but I know where it is horizontally. So I can get a y value 2 different ways. I can either count the parabola pattern, or I can stick the x value into my equation and evaluate it at 6 to see what the y value would be. Now I'm going to do that just again because it's going to prove a point. So I'm going to take my function. I'm going to evaluate it at 6 because that's where my axis of symmetry is. So I would end up with 6 squared minus 12 times 6 plus 27. Maybe not a good idea to do it there. But so f at 6. 6 squared is 36. 12 times 6 is 72. It's going horribly wrong here. Maybe not. 36 minus 72 would be negative 36. And negative 36 plus 27 is negative 9. So my vertex vertically is happening at negative 9, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Down there. Now there are some dots I could put in here in a careful pattern, but I'm not really concerned about a beautiful sketch here. I was really just after the maximum or minimum value. So this parabola is going to do something like that. It's a terrible sketch, Jared. You can do better than that. Gross. But lo and behold, there is the lowest point, and it happens to be at negative 9. So I was able to take my standard form, use the quadratic formula to get the x-intercepts, plot them, look for the axis of symmetry, and then plunk that back into the function in order to get my maximum value. Well, that's fine, but this actually told you where the axis of symmetry was. And it happened right around here. So I'm going to take this part of the quadratic formula, and instead of writing it as a single fraction, I'm going to write it like this. Well, square root of 36 is 6, so I'm just going to do that in the same step. So 12 divided by 2 is 6, and 6 divided by 2 is 3. So when you're trying to find the x-intercepts, you ended up with a structure like this in your quadratic formula, which told you where the axis of symmetry is, and how much you have to step away from it in order to find your x-intercepts. Now that, like, if you take a minute to think about that, I mean, obviously, right, if you're trying to find these two spots, you need to get to the place in the middle and either step up this much or step down this much to get to those x-intercepts. Because of the symmetry, you have to have a center and then a deviation from the center. So that's great. What if we could do this without having to go through all this quadratic formula stuff? So I'm gonna take this down, get it out of the way, because we know that this works now. And I want to track where this 6 came from. To do that, I'm going to get rid of the specific numbers up here. Kind of gross. Threw my brush on the floor a minute ago, and now I desperately need it. Okay, what are we doing? Gotcha. I'm going to take this quadratic formula, and I'm going to write it as 2 fractions instead of 1. So instead of this plus or minus that, it would be negative b over 2a plus or minus the b squared minus 4ac over 2a. All right. So if I take this and split it as 2 different fractions, I've got a number plus or minus some other number. And this thing in front, that's going to be the location of the axis of symmetry. Right? In this particular example, it would be 12 divided by 2 times 1, which is 6. This piece here is the sort of deviation, starts with a D, not a B. It's going to be a long day. The deviation to find the x-intercepts. So you could tease the quadratic formula apart into those 2 pieces. And if you're knowing that this is where the axis of symmetry is, then you have the x value for the vertex. It's just sitting right there, negative b divided by 2a. And if you're after the max-min, right, the actual y value, we took the x values, right, the x value is the axis of symmetry, and plunked it back into this equation. And if you remember, it was 6, so I put a 6 here and a 6 here and worked out negative 9. Well, I'm going to do that with this. So this function evaluated at negative b over 2a. So I would need to put a negative b over 2a here and square it, minus 12 times negative b over 2a plus 27. Okay. Now, I put in a generic axis of symmetry, so I want to make this into a generic parabola. So I'm going to have to acknowledge that there should be an a value here. This would be your b value, and this would be your c value. Okay, now, good Lord, there's a lot of letters there, but this is every parabola. Doesn't matter what's here or here or here. The truth of the relationship is all in there for every parabola you could ever invent. Might be an upside down one if this was negative. It might be a really tall one if this is 2 or 5 or 10. It might be a really short fat one if this is 1/2 or 1/3 or 1/10. It doesn't matter. It's every parabola you could ever imagine. So whatever we cook up out of this is going to be a universal statement about any parabola you ever come across, which ultimately is the point of doing all this math analysis. It's, can I take a model, a specific model, think about how it works, find out something in general about it, like this is always the axis of symmetry, and then try and cook up some other facts based on this universal statement so that you know everything about every parabola that can ever exist, right? Like that's really powerful if you think about it. What are we doing? Okay, I'm going to expand this here, and I'm going to go with one color because the many colors will just slow me down and scramble my brain at this time of day. So I've got an A here. Negative b squared is b squared. The negative times a negative is positive. 2 squared is 4. A squared is a squared. I have a b times a b. That's a negative b squared over a 2a. And I have this plus c back here. Now an a divides an a. So I end up with a b squared over top of a 4a. I have a negative b squared over 2a. Now these things are almost fractions with a common denominator, so I'm going to adjust it so they do. If I doubled this, I would have 4 on the bottom. If you double the bottom, we've got to double the top. So I have b squared minus 2b squareds. That would be a negative b squared over 4a. And it's kind of rude to lead with a negative, so I'm going to switch the order around here. C minus b squared over 4a. So every parabola, doesn't matter what the numbers are up here, if you have it in standard form, that's the x value of its vertex, and this will be its maximum value. Now, if you remember back, this one, the max value was -9. Sorry, the min value is -9. So I'm just going to test this by taking these numbers and parking them in there. So let's see. My min value should be the c, which is 27. Subtract the b squared, I'll just write it in there, over 4 times the a value. End up with 27, subtract. Negative 12 squared is 144. 144 divided by 4. 100 divided by 4 is 25. 44 divided by 4 is 11. 25 and 11 would be 36. And like magic, 27 minus 36 is -9. Boom. So, what's the point? Remember all that quadratic formula stuff I had to do in order to find the x-intercepts? And then I had to draw a picture, and I had to plot the x and the x-intercepts to find the axis of symmetry. Then I had to take the axis of symmetry and put it back into the equation in order to get this min value. Well, with a little bit of thinking and a general case where I used the coefficients instead of specific numbers, I was able to use the quadratic formula, which we know works, to find where the x-axis or the axis of symmetry would be, and hence the x value of the vertex of any parabola. And then I plunked it in there to end up generating a formula for the max min value of any parabola. So all that analysis technique you've been learning, I mean, you could have just done this and just had a formula for it. So why did you have to do it? Well, because none of this would make any sense if I tried to convince you that this worked. If you didn't know how to complete the square and solve for 0 in order to generate this in the first place, yada, yada, yada. But I have been able to generate this using those techniques. And it makes you wonder, if I can do this to a parabola, can I do it to an exponential? Can I do it to a logarithm? Can I do it to sines and cosines? Can I do it to functions that are combinations of those functions? And the answer is, of course, yes, once you have the right techniques, right? This was a parabola specific feature, so we will have to have techniques to generate this thing, like the starting point for each individual function. But it is possible to just crank it out like this. And if you can do that, then when you get into software programming, if you need to generate the max min values of anything here, you can just plunk this formula in. Instead of asking your computer to have to run iteration after iteration after iteration of nudging up calculations trying to refine its answer, you can just get it to hack one arm because you understood the model well enough to be able to instruct that machine on how to find it. Okay, so this idea here is sort of pre-calculus, right? It's the idea that every function has a generic model you can use in order to crank out a generic answer for some feature of it. For the practice problems, we're just using this and we're using that in order to find max min values of different parabolas that have fraction coefficients or negative coefficients or what have you, so that you can try and do some of this analysis.